Hi, my name is Piotr Sarna, and my talk is a case study on how getting rid of WebAssembly is great for your latency, and more specifically, how you can reduce the size of your WebAssembly binaries so that they load faster and perform better. I spent a few years hacking on ScyllaDB, which also includes the early days of introducing WebAssembly as an engine for user-defined functions. And now I'm working at Turso and also maintaining the libSQL project, which is an open source contribution fork of SQLite, the well-known database library. A word of introduction first. WebAssembly is already a standard for optimizing web applications and making them super powerful. So compiling games like Doom isn't out of the question for browsers now, which is amazing. And what's even more interesting is that WebAssembly is emerging as a standard for virtualization. Platforms like Fermion Spin or Cloudflare Workers already let you run server code powered by WebAssembly. And the WASI standard, which stands for WebAssembly System Interface, is something that gives Wasm apps standardized access to resources like input-output devices and network, and that makes them pretty much just as powerful as any other computer program. In any case, an application must be compiled to Wasm first, and Rust is a very decent choice for that. It supports compiling to both plain WebAssembly and the one based on WASI. Comes with lots of convenience tools and is very ergonomic, just like the rest of the ecosystem. But if you're not careful, the code you'll get from compiling Rust to Wasm can be bloated out of proportions. Rust is a rich ecosystem, which makes it a fantastic developer experience. But it's also very easy to end up with tens or hundreds of dependencies in your otherwise small project. Another thing is that WebAssembly apps tend to be self-contained, so they don't link dynamically to shared libraries and things like that, and instead contain all the code that they need to run. And that becomes problematic when you have to handle thousands of those Wasm programs, and each one contains identical copies of some standard library code, which is often not even used. Debloating the size of your compiled binaries has a charming name, minification. There are many aspects in which shrinking your programs is beneficial, and the most important ones are as follows. First of all, if you use less resources per application, you can run more of them on a single piece of hardware. If you're running, for instance, user-defined functions in your database, it's good if the footprint of the Wasm code is as small as possible, because databases tend to be very short on resources in general. Then, before running a piece of Wasm code, you need to load it into memory first. And as you can imagine, loading a few kilobytes is simply faster than fetching tens of megabytes from your disk or over the network. And finally, if you have less code, it usually translates to your app running faster. You have less instructions to execute, more of them fit into processor caches, and so on. I hope I've convinced everybody already that making sure that your apps are not bloated is a worthwhile investment of your time, WebAssembly or not. Let's go over a few things you can do to minify your compiled WebAssembly apps. Some low-hanging fruit first. Compiler configuration options that help keep the output binary small. First step, maybe obvious to some people, disable debug information. It's actually the top offender and really crucial if you need to handle lots of WebAssembly instances. Debug symbols produce megabytes of data that is definitely useful, but also very costly to keep. Next, there's link time optimization. That's an opportunity for the compiler to deduplicate more code, which often makes it not only smaller, but also more efficient. Then set the optimization level to S, which stands for size. Note that there's also a Z optimization level, which stands for aggressive size optimization. But I personally found it to be so aggressive that it actually produced larger binaries than the regular in all of my test cases. So I just passed on that one. It might work for you though, so give it a chance at least. Finally, turn on abort on panic mode, which disables stack unwinding when something bad happens and instead just kills the program immediately. And that's often a reasonable choice anyway, especially for short-lived programs like user-defined functions. Turning on panic equals abort option is also a prerequisite for a more complex minification trick, which I'll describe on the next slide. Next, you might be tempted to just drop the standard library. That shaves off lots of code, but at the expense of developer experience. Coding WebAssembly apps in Rust would not be as ergonomic if you weren't allowed to use strings or vectors, allocate memory, and so on. Also, lots of Rust crates assume that the standard library is available as well, and they simply won't compile if we opt out of it. So as a middle ground solution, you can rebuild the standard library with simplified panic handling, and that's good enough for most cases. It's also worth pointing out that it wasn't enough to turn on this abort on panic mode in cargo toml file on the previous slide, and only recompiling the standard library will actually get rid of the code from the final binary. This custom build script you see on the slide also contains one more trick, a J1 flag. This flag sets the number of so-called code gen units, which stands for code generation units, to 1. That makes the compilation slower, but the optimization step is more thorough, being able to take all the existing code into account. So it gives the compiler more opportunity to deduplicate common paths, and that may also contribute to reducing binary size, as well as better performance on runtime. Then the binarian project has some real goodies. Wasm opt is a post-compilation optimization tool that can also take an S flag, which stands for size optimization, and it works wonders. I highly recommend it to everyone. It can also take a Z flag for aggressive size optimization, and I, again, encourage you to try it, but standard S is a safer choice since Z is allowed to sacrifice runtime performance for size. Next, Wasm strip. Wasm strip removes custom sections from the output WebAssembly binary. And I specifically said custom sections instead of debug symbols, because even if you compiled in release mode and without any debug symbols, Wasm strip tends to trim the binary even further. So it's always worth giving it a go as well. Then, while experimenting with binary size and searching for the ways to minify my programs even further, I stumbled upon Twiggy, a size profiler for compiled WebAssembly, and I really liked how easy it was to inspect the binaries with it, so let's go through some examples. Twiggy top gives you a list of top offenders. I ran the example you see on the slide on a non-optimized user-defined function which encrypts a string. And you can see that around half of the code is something else than the function logic. So it sounds like there's room for improvement. After all the recompilations, Wasm opt and Wasm strip, you can get encrypt to take over around 95% of the total binary, which is precisely what I wanted to achieve. Bare minimum to run the logic we need and nothing else. Twiggy dominators gives you a dominator tree of the call graph, which lets you know which symbols are visited the most. It lets you detect what are the likely hot paths in your code just by performing static analysis of the code. In our example encrypt function, this is the expected output. We only implemented a single function, so that's what should be listed here. Although around 10% of the path is occupied by dlmalloc, which is the default allocator for the WebAssembly target in the Rust ecosystem. And that part can also be optimized, and I will mention it in a few slides. Twiggy garbage lets you know if there are any symbols or sections, dead code, etc., that aren't useful and could be thrown away from your binary to reduce its size. Wasm strip and Wasm opt will generally take care of that all, but Twiggy garbage is still important for analysis as well as continuous integration. It's definitely worth adding to your CI scripts just to have a regular report of how much waste your project contains. Now, allocators. WeAlloc is an allocator implementation that's way more lightweight, I think 10 times at least, compared to dlmalloc, which is used by default, as you may have seen in Twiggy output from previous slides. And WeAlloc is implemented with simplicity and correctness in mind, as well as small code size. So it's likely not the fastest allocator around, but it's also likely that your WebAssembly application doesn't need lots of allocations in the first place. So it doesn't need the very fastest allocator in the world. Maybe your allocations are short-lived because it's just a user-defined function, and maybe it only ever needs to allocate some strings up front and then doesn't allocate anything else. And for that purpose, it is a net gain to just use a simple, correct, and really, really small allocator rather than a general larger one. And then, in those cases, WeAlloc is a great choice. Wasm snip is another interesting program. It's one of the tools used by people who insist that they are smarter than their compilers. And well, sometimes, not often, they are right. Wasm snip cuts a function out of the binary by replacing it with an unreachable instruction. That's the kind of thing that your compiler should either inline or optimize out. But if for any reason it cannot formally prove that the function is actually unused, its code will end up being there in the output binary. For that particular case, you can use Wasm snip to cut the function out. There may be some standard library boilerplate in your binary that's actually unused, and Wasm snip will help with that. And it can also be used as a tool for aggressive optimization. For instance, you can randomly pick and cut out a function and see if the code still runs fine without it. That's, of course, dangerous and not advised for production code, but on the other hand, perfectly reasonable for minifying test cases. And speaking of that, Wasm reduce is a very interesting tool. It runs various transformations, some of them breaking, to create a minimal Wasm program that still works correctly according to the checker command that you provide. And it will most certainly ruin production code, but on the other hand, it works great for minifying test cases, especially for fast tests. And often there are thousands of those, so if you minify every single one, your gains may be substantial. The way Wasm reduce works is that it keeps transforming the code, then running the checker command, and then deciding what to do. If the checker command reports that the program still works, then we can continue reducing. And if it failed, we must roll back and try another transformation. It is also really educational to read logs that Wasm reduce produces and see what kinds of transformations are applied. And that's because some of them are not breaking and include, for instance, removing debug symbols and running Wasm opt the post-compilation optimization tool. Other transformations are breaking and they rip whole functions off of the program, Wasm snip style, and just check if it still works fine. If it does, then this function can be ignored for testing purposes, and that saves space. Time for some numbers. This table shows the steps from a very naive debug build of the aforementioned encrypt function to a proper size optimized output. The vast majority of the bloat was removed by simply building in release mode without debug symbols, so no surprise there. But even that is not even close to the final result, as you can see from the table. Starting with a release build, you can still go 8 times smaller by applying these few relatively simple tricks. The last 4 kilobytes were squeezed out of the binary by switching to another memory allocator, walloc. And I bet you can spend even more time here to reduce the size even further. And if somebody knows how, please reach out to me. But for our purposes, 20 kilobytes is already perfectly acceptable. So we stopped at that. Here are some more examples of how minification helped us. The encrypt function I already covered on the previous slide, but on top of that, we also trimmed the test cases we use quite substantially, especially that this reduction was per single test case, and we have like a couple of hundreds of those. So it starts to actually matter. And then, even more importantly, our online playground for libSQL, which is an SQLite fork, is based on this idea of having the whole database engine compiled to WebAssembly and then running from users' browsers. The default build for that was 3 megabytes, which is already super impressive for a whole database engine implementation. But it was also enough to cause a small latency lag when users first loaded the site. Once the size was reduced to a couple of 100 kilobytes, applying the tricks from the presentation, the latency issue was way less severe, even for users with reduced bandwidth. Thank you. If you enjoyed the presentation, feel free to reach out to me. And if you didn't, feel free to reach out anyway.